Good morning. My name is Velimir Rothschild, and I am the author of this short Instrumentation Basics course. Course objective is to test Kazakh instrumentation workers basic instrumentation knowledge in order to prepare them for smooth loop checking and instrumentation quality supervision tasks. The course may be useful to test foreign workers and to general audience too. It is entirely on DVD, enabling anyone who wants to learn instrumentation basics to do it anytime, anywhere. It contains also various useful information literature, a short video course of English language, and a small Russian-English video dictionary of instrumentation terms. I will never forget the message of one of my professors at Electrotechnical University of Zagreb, Croatia, the first day of lessons more than 45 years ago. He said, "You can achieve success if you apply your imagination and energies to drive your motivation. Who dares wins." This message was and still is my guideline in my approach to life and work. It means that everyone must always have a goal, and this goal can always be reached if the one who set it wants to reach it, no matter how difficult it is. This means also that the majority of the problems in the life and in the work can be overcome simply if the one wants. My second message is safety in working place and life. We work in a potentially dangerous environment, and we must be aware of all dangers of working place and strictly follow safety rules and guidelines. I was present at the beginning of my work in an oil refinery and witness to an accident when a friend of mine lost his left eye in an explosion. Since then, safety and accident prevention became my priority. This means personnel must always wear in the field personal protective equipment. In order to prevent accidents, the technical personnel must be aware of responsibilities. They must have a good understanding of work permit system, must have a detailed working knowledge of work permit procedures as it applies to his own work. Ensure he does not begin any work requiring work permit until it has been authorized and issued. Ensure that he fully understands and adheres to the conditions and safety precautions in the work permit. My third message is friendly human relationship in workplace and life. The life on work is much better, and work performance greatly superior if problems are solved in mutual respect and good human relationship. In other words, my message is teamwork and the concept of integration. Everyone must be aware of his task within the company and contribute to its overall success. My fourth message is the importance of training and constant learning. The technology constantly changes at a great pace, and if one does not follow it, it gets lost, and exactly as a machine becomes obsolete. Therefore, one must be restless and receptive to new ideas. My fifth message is the importance of knowing English language. English language is the language in any oil field. My sixth message is the importance of being computer literate. Today and in future, computers are and will be present everywhere, and one must understand how to use them. My seventh message is never to be afraid to ask questions, and let each success springboard you to an even greater success. And finally, my personal message is that to endeavor any mission in life, it is essential to know that it is not the beginning but the continuing of the same until it be thoroughly finished, which yields to the true glory. In other words, if you start something, you must have the determination to complete it. Let me speak now a little bit about learning process. Instrument job is one of very well paid jobs. Instrument technicians and engineers are very and will be for many years ahead required, especially in Kazakhstan. To become a good instrument specialist, there are some essential requirements. Good knowledge of English language, good knowledge of computers, writing and saving files, and knowledge of instrumentation. Technical English is not difficult. The grammar is very simple, and there are to be learned not more than 1,000 words. After attending a simple English course, one may proceed on his own. It is necessary to learn every day only a few new words. It's a very good practice to listen often shortwave radios in English and to watch English-speaking stations on TV. To learn to work with computer is not difficult. It is necessary to know to write, save and move files, and know how to use electronic mail. First approach to learn instrumentation are theoretical lessons, which represent 10% of necessary instrumentation knowledge. Practical or on-job training is the most important, but it comes only after theoretical training. Instrumentation is practically not a manual, but highly intellectual work. It is always necessary to understand what is being done. So, if you do not understand, do not do it. To learn theory, it is not enough only to listen, it is necessary to study. to study a good literature is necessary. Learning is a continuous, constant process. If you do not study constantly, you will not progress. The topics learned need to be repeated constantly, otherwise they will be forgotten. The biggest challenge in teaching and transferring knowledge is to make knowledge understandable. Many problems or accidents occur due to poor knowledge, due to bad instructions. Instructions must be simple and understandable. Introduction to instrumentation. Instrumentation is the science of measurement and control. Measurement is the comparison between the unit entity and measured entity. If we say that a table is 2 meters long, we compare the length of the table with the unit of length 1 meter. Control is keeping measured entity at desired value or set point. Once again, measurement is the comparison between the unit entity and measured entity or quantity. And control is keeping measured entity or quantity at desired value or set point. In a plant, this means, for example, to keep the level of a tank at 60% of its maximum level. Process plant is the plant where process materials, for example, mixture of oil and gas, are being treated to obtain semi-finished or finished products, crude to be transported through pipeline. Process plant operates following a recipe or technology in the same way as a recipe to prepare food. Further, to run the plant, civil works and electrical, mechanical and instrument equipments are necessary. Further on, some forms of energy, electrical, energy from gas or oil, is necessary. And finally, the most important factor to run the plant are people involved in plant's operation. Instrumentation constitutes 10 to 20% of value of a plant. If we compare a plant with human body, instrumentation is the brain, the eyes, the nose, the ears, the hands and the legs. So it can be seen how instrumentation is a vital part of a plant. To understand instrumentation, it is essential to understand 4 fundamental topics: international systems of units, SI, instrumentation basics, instrumentation symbols, and explosion protection of electrical instrumentation. International System of Units SI. The 11th General Conference on Weights and Measures, meeting in Paris, birthplace of the metric system, in October 1960, formulated a new international system of units, or SI, which is now used officially in all countries except in the USA. Its 7 basic units, from which all other units are derived, are currently: for length, the meter; for mass, the kilogram; for time, the second; for electrical current, the ampere; for thermodynamic temperature, Kelvin; for luminous intensity, candela; and for amount of substance, mole. The unit of length, 1 meter, was defined as 1/10,000,000th of the distance between the equator and North Pole. Due to increased accuracy, today it has a different definition. 1 kilogram is the mass of 1 cubic decimeter of pure water. 1 second is 1 hour divided by 3,600. 1 hour is a day divided by 24. 1 day is the time of rotation of the Earth around its axis. 1 ampere is the unit of electrical current which produces a defined force between 2 parallel conductors distant 1 meter. 1 degree Kelvin is 1 divided by 273 of the temperature of triple point of water. Triple point of water is a mixture of ice and air, saturated water at a pressure of 100,000 Pascal. I will not comment the last 2 units because they are practically not used in instrumentation. All other units are derived from base units. There are precisely 22 derived units. In instrumentation, we will only meet a few of them. The following definitions are very important and must be learned. Force is one of 22 derived units. It is defined by the second Newton's law. Force equal mass multiplied by acceleration. force is mass multiplied by length divided by time on the power of 2. And unit of force is called Newton. Newton is the unit of force which gives the mass of 1 kilogram an acceleration of 1 meter in the second to the power of 2. Let us learn another unit. Work or energy is defined as force multiplied by length. Unit of work is, per definition, the work obtained by moving a mass of 1 kilogram for the length of 1 meter. Unit of work is called joule. Joule is equal of 1 Newton multiplied by 1 meter. The work performed in a certain time is called power. Power is the work divided by time. The unit of power is watt, and watt is joule divided by second. We can also express joule as watt multiplied by second. 1,000 times greater unit of watt is called kilowatt. We have learned force, work, or energy, and power. Let us learn another derived unit. If we raise the length to the power of 2, we get the surface. The unit of surface is 1 square meter. If the force is applied to the surface, another unit is obtained called pressure. Pressure is force divided by surface, and a unit of pressure is called Pascal. Pascal is the force of 1 Newton applied to the surface of 1 square meter. Pressure is the unit very much used in instrumentation. Pascal is a very small unit of pressure, so practically we use a 100 times greater unit called bar. 1 bar has 100,000 Pascal. In instrumentation, further than pressure, we use only 3 more entities or quantities: temperature, flow, and level. Temperature is one of 7 base units of SI system of measuring units. The unit of temperature is Kelvin. For practical use, another unit is used called Celsius. Celsius is Kelvin minus 273. Flow is the volume or mass passing through a certain section in a unit of time. Flow is expressed in kilograms per second or liters per second or its multipliers. Level is the height of a liquid in a container. It is measured in meters or percentage of a maximum level. The SI system is based on multiples and submultiples of 10. Greek prefixes are established for multiples of 10. Mega means 1,000,000, kilo means 1,000, hecto means 100, deca means 10, while Latin prefixes are selected by submultiples. Milli means 0.001, centi means 0.01, and deci means 0.1. Measurement error. It is impossible to achieve total accuracy of measurement of any entity or quantity. A measurement error is always present. There are three definitions of errors and a definition of class related to measurement error. Absolute error is the difference between the measured value and true value. Relative error is absolute error divided by measured value. Percentage error is relative error multiplied by 100 and expressed in percentage. Instrument class is absolute error expressed as percentage of instrument scale. Example: absolute error of a pressure gauge of the range 0 to 10 bar and class 1 is 1% of 10 is 0.1 bar. Absolute error is always expressed in units of measurement of an instrument. In our case, units of measurements are bar, so absolute error is expressed in bar. Class 1 means that absolute error of the pressure gauge in example is 0.1 bar. If pressure gauge has the scale of 0 to 16 bar and its class is again 1, its absolute error is 1% of 16, it means 0.16 bar. If its class is 2.5, its absolute error is 2.5% of 16. 2.5% of 16 is 0.025 multiplied by 16 is 0.4. Class 2.5 of a pressure gauge with the scale of 16 bar means that the pressure gauge has an absolute error of 0.4 bar. Pressure gauge of class 1 and scale 10 has the relative error at the scale end of 0.1 divided by 10 or 0.01. Relative error at the middle of scale is 0.1 divided by 5 equals 0.02. 0.02 is twice so big as 0.1. At the middle of scale, relative error is double than at the top end of the scale. It is very important to understand that every instrument has the greatest accuracy at the top end of its scale. Instrumentation basics. It has been said in introduction paragraph that instrumentation is the science of measurement and control. And it has been explained what is measurement, what is control, and what is process plant. Let us go a little bit further, explaining in more details what is control. Let us examine flow control. On the picture we see 4 elements: orifice plate, flow transmitter, controller, and control valve. We see that flow can be controlled with 3 elements: flow element, orifice, and flow transmitter, flow controller, and control valve. Orifice causes pressure drop proportional to flow. Pressure drop is detected by pressure drop transmitter, which converts it to a standard communication signal and sends it to the controller. Controller has 1 input, 1 output, and a set point. If the input measured value of flow is different from set point desired value of flow, output signal is created to change control valve opening in order to raise or decrease the flow to make it equal to the desired value or set point. These 3 elements, transmitter, controller, and control valve, constitute control loop. There is another element of instrumentation. It is called information. In fact, it is necessary to know the amount of flow, the so-called settings of controller, and the opening of control valve. Today, information is represented on a screen of a monitor. Now we can say that instrumentation is constituted of 4 items: transmitter of process quantity, controller of process quantity, control valve, and information entity. Less than 100 years ago, processes have been controlled manually. Then, 70 years ago, appeared first controllers. 60 years ago, appeared the first control room and pneumatic instrumentation. Pneumatic instrumentation uses compressed air as the energy for its operation. Every transmitter had its indicator and every control loop had its single controller. 40 years ago appeared analog electronic instrumentation. 32 years ago, a revolution took place with the appearance of Honeywell TDC 2000 digital distributed control system called DCS, with the introduction of digital controllers controlling several control loops at once and television monitors instead of indicators. 19 years ago appeared the first digital or smart transmitters. Today, the trend is complete digitalization, standardization, and information not confined to control rooms, but available in the local computer network. Field instrumentation. Field instrumentation consists of process measuring instruments, fire and gas detectors, and vibration instruments. Process measuring instruments comprise flow, pressure, level, and temperature meters and control valves. They also include process analyzers, which measure pH, conductivities, and stack gas content. Fire and gas detectors detect or measure fire and presence or concentration of flammable and toxic gases. They comprise also fire and gas sounders and lamps, red for fire, yellow for gas, and manual call points. Vibration instruments measure vibration of rotating equipment, that is, motors, pumps, compressors, and turbines. And the relevant vibration system produces alarms and stops the equipment in case of high vibrations. In order to work, instruments need electrical power supply. Only control valves used compressed air or pneumatic power supply. In this case, they are called pneumatic control valves. Electrical instruments communicate between them by means of electrical signals. Signals may be analog, and in this case, they are in the form of direct current DC of 4 to 20 milliamperes. Power supply for analog communication signals is usually 24 volts DC. Communication signals may be also digital, and for the time being, there is no unique digital communication standard. Pneumatic signals are in the form of pressure 0.2 to 1 bar, and pressure power supply is usually 1.4 bar. To move control valve, electrical control signal is converted into pneumatic by means of I to P current to pressure converter. The above picture shows process control of a plant. Full line in the picture may be a so-called field bus, that is, many incoming and outgoing cables to and from DCS, distributed control system. DCS is a controller with its inputs and outputs from the field and monitors on which process data are shown. Emergency shutdown system. A plant has a separate emergency shutdown system. It is nothing else but another DCS control system, which function is to control the stopping of the plant in case of an emergency situation. It has similar elements as DCS system, that is, field instruments which are mostly fire, smoke, or flammable and toxic gas detectors, but also process instruments which, in case of plant abnormal operation, initiate plant shutdown, and as the output, control valves, which are now called shutdown valves, and switches to activate various shutdown equipment and sirens. ESD system has no proper monitors, but uses generally DCS monitors to show ESD informations. Vibration monitoring. All major rotating equipments have vibration transmitters connected to vibration system, which in turn is connected to ESD or DCS system, either for monitoring, either for shutdown. On this picture, we see the schematic representation of all three systems. Field instrumentation is connected to DCS. All data are represented on monitors. Fire and gas sensor manual call points are the inputs to emergency shutdown system. Also, rotating equipment vibration sensors are connected as the output to ESD system. Output of ESD system are sirens, lamps, and ESD valves. Input to the ESD system comes from vibration system. Documentation, process diagrams. Many documents are issued during the development of a plant project. The main ones are block diagrams, process flow diagrams, and the most important, piping and instrument diagrams, PID, location plan, data sheets, loop diagrams, manuals. A block flow diagram is a schematic illustration of the major process elements. The block or rectangles represent a unit operation. The blocks are connected by straight lines, which represent the process flow streams, which flow between the units. A process flow diagram is a schematic illustration of the system. It shows the relationships between the major components in the system. It also tabulates process design values for the components in different operating modes, typical minimum, normal, and maximum. A piping and instrumentation diagram, PID, is a schematic illustration of functional relationship of piping, instrumentation, and system equipment components. Location diagram shows the position of various, for instance, instruments in the plant. Datasheet is the identification document of an instrument with its process, mechanical, and electrical characteristics. Loop diagrams show all the connections of an instrument. It is divided in two sectors, field and control room. Field is divided in subsectors, instrument, junction box. Loop diagram is essential for the whole instrument connection for the installation and maintenance. Manuals contain every information concerning the plant and instruments operation. Instrument identification. Instrument identification is composed of 2, 3, or 4 letters, of which the first letter always indicate the process variable measured by the instrument. L for level, T for temperature, P for pressure, F for flow. It is also possible that the first letter is an A, which means that the instrument is an analyzer. The second letter can actually be a group of letters which represent the function of the instrument. T for transmitter, I for indicator, C for controller, R for recorder. For example, PT is a pressure transmitter. PI is a pressure indicator. PIC is a pressure indicator and controller. PRC is a pressure recorder and controller. There are 4 graphical elements of a PID. Discrete instruments, DCS, distributed control system, PLC, programmable logic controller, and ESD, emergency shutdowns functions. Discrete instruments are indicated by a circle. DCS functions are circles surrounded by a square. PLC, programmable logical controller, functions are indicated as follows. ESD, emergency shutdown functions, are also indicated as follows. Instrument lines designation. Full line, instrument directly connected to the process. Dotted line, electrical signal. Hydraulic signal, pneumatic signal, capillary tubing, internal system link. Ohm's law. Voltage is equal to current multiplied by resistance. Per definition, power dissipated in an electric circuit is P equal V per I. It means power is equal to tension multiplied by current. What is the unity of power? The energy consumed in an electric circuit is, per definition, power multiplied by time. Energy equals power by time. The unity of energy is watt per second. If the current flows always in one direction, it is called direct current or DC. Direct current is for now used for instrument communication. There is a standard current communication of 4 to 20 milliamperes at 24 volts power supply at 0 to 600 ohms circuit resistance. The communication with DC current is also called analog communication. If the current changes its direction, it is called alternate current or AC. There is another type of communication constituted of direct current pulses. This communication is called digital communication. All world communication is now digital. Only in instrumentation there is some analog communication. At SGP, all field transmitters use digital communication called HART. Process signals. Pneumatic signals. Pneumatic signals are transmitted over the scale of 0.2 to 1 bar. They are carried by tubing, usually PVC coated quarter millimeter or 3/8 inch diameter copper or stainless steel tubing. Maximum transmission distances are limited to at most 200 meters. Electric signals can be categorized into continuous and digital. Continuous electrical signals are transmitted as a current 4 to 20 milliamperes over shielded pairs of wires. Nowadays, many sensors and instruments are digital devices, taking in and sending out digital signals. With such devices, signals are transmitted as series of electrical pulses. That is, the signal is essentially two-state, high-low or on-off. Transmission is usually via pairs of wires, although use of optical fibers is becoming more and more common. The entire transmission is commonly known as the communication protocol. In general, different manufacturers adopt different communication protocols, although there is a strong move towards an industrial standard. There is no standard digital transmission protocol yet. HART protocol is the oldest and the most used digital protocol. With HART protocol, the traditional analog signal of 4 to 20 milliamperes is superimposed with digital signals. Field instrumentation details. As already said, instrumentation is the science of measuring physical entities, mainly 4 of them, and that is pressure, temperature, level, and flow. Let us begin with explaining pressure. Pressure is force divided by surface. Unit of pressure is called Pascal, and it is the force of 1 Newton applied to the surface of 1 square meter. Pressure is the quantity very much used in instrumentation. Pascal is a very small unit of pressure, so practically it is used a 100,000 times greater unit, and it is called bar. 1 bar equals to 100,000 Pascal. Pressure can be measured locally by devices called pressure gauges. In many cases, pressure and other process variables must be indicated in control room. To accomplish this task, process transmitters are used. They measure, for example, pressure and transform it into an electric signal, which at SGP is HART, and it has been already explained that digital HART protocol is superimposed to the analog 4 to 20 milliamperes DC signal. Electric signal goes to an indicator, or in most cases to DCS monitor. We see the picture of a differential pressure transmitter used at SGP. The lower part is connected by usually stainless steel pipes to the pipe. The upper part produces an electrical signal proportional to the applied differential pressure. Flow is the measurement variable which shows the quantity of gas or liquid passed through a pipe in unit of time, which is an hour or a second. The quantity may be expressed in volume units, cubic meters per hour, or cubic meters per second, or mass units, kilograms per hour or kilograms per second. The most common flow measurement is by inserting in a pipe a restriction in a form of an orifice between two flanges and measuring the pressure drop caused by it. Pressure drop is proportional to the square of the flow. The above differential pressure transmitter is connected to high and low pressure sensing line. There are some other types of flow measurement devices, as for example electromagnetic and variable area flow meters, but they will be not discussed in this session. Level. Level is the process variable which shows the height of the liquid in an open or closed tank or vessel and is measured in millimeters, meters, or percent of the maximum level. The same differential pressure transmitter may be used not only for pressure flow but for level measurement too. We see an example of level measurement in an open tank and in a closed tank. Here is the picture of an ultrasonic level transmitter, and here the picture of radar level transmitter. Temperature. Temperature of an object is its level of hotness or coldness. Temperature is one of 7 base measurement units. Temperature unit of measurement is Kelvin. For practical use, Celsius is used. The relationship between Kelvin and Celsius temperature scale is Celsius is equal Kelvin minus 273. Two sensors are used for temperature measurement: thermocouple and resistance thermometers. Thermocouples consist of two dissimilar metallic conductors joined at the point of measurement. When the conductors are heated, a voltage is generated, and this can be used to determine the temperature. Produced voltage is proportional to the difference in temperature between the junction junction and the open end. Resistance temperature detectors, RTD, are based on the principle that electrical resistance of many metals changes with temperatures. Metals for which resistance increases with temperature are used in RTDs. Temperature can therefore be determined from the change in the electrical resistance of the metal wire. Generally, a temperature transmitter is connected to the thermocouple or resistance thermometer so that 4 to 20 milliamperes or higher protocol signals are produced proportional to the temperature. Below is the picture of the temperature transmitter connected to the thermocouple or RTD sensor. Controller. The mission of controller is to make the measured value, usually known as process variable, equal to the desired value, usually known as the set point. Controller has two inputs, set point and process variable, and one output, signal to control valve. At SGP there are no single controllers as on the picture, but the controllers are incorporated as software functions within the DCS system with the same function and action as on this picture. The process operator sees on the DCS monitor a similar picture as on the controller, and that is the set point and process variable. Control valves. Control valves, or final control elements, are the third element of the control loop. The purpose of the control valve is to reduce the section of the pipe where the control valve is installed in order to control the flow of a fluid through the pipe. In such a way, not only flow, but pressure level and temperature may be controlled. Control valves may be continuous and on-off. Continuous control valves may assume any position, that is, they can reduce the section of the pipe from the total close to the total open position. On-off control valves may assume only two positions, open and closed. Depending on the energy used to move control valves, there are pneumatic, electric and hydraulic control valves. On-off control valves are usually pneumatic. Controllers produce electric signal which is converted into pneumatic by current to pressure transducers in order to move control valve. This is the picture of pneumatic control valve, and this is I to P converter. Fire and gas detection. Although fire and gas detection has the same attributes of instrumentation, it is always dealt separately, but involves instrument people. It has fire and gas sensors and transmitters using the same 4 to 20 milliamperes or digital output signals. It has no single loop controllers. In fact, at SGP, there are no single loop instrument controllers at all. All control is performed within a separate DCS. Instrumentation uses Honeywell TPS, Total Plant Solution DCS. Fire and gas system uses ICS triplex DCS called Emergency Shutdown System or ESD. Control valves are only on-off. Other final control elements are electrical motors, sirens, and visual alarm beacons, red for fire, yellow for gas. There are three characteristics of fire: flame, light, heat and smoke, and so are the relative detectors. There are flammable and toxic gases. At SGP, toxic gas is mostly hydrogen sulfide, H2S, and sometimes methane. Fire and gas symbols are summarized next. NHR, rate of rise heat point detector. NSO, optical smoke detector. NFD, combined infrared and ultraviolet flame detector. NGC, combustible gas detector. At SGP, flammable gases, that is gases produced by fire, are detected by Draeger Polytron IR infrared gas detectors. These detectors are installed either standalone, either in aspirator cabinets. In the latter case, flammable gases from stacks or other ducts are aspired and brought to the detector through small tubes. The output of toxic gas transmitter is 4 to 20 milliamperes and hard, and can be thus checked by hard communicator. The 4 to 20 milliampere output is configured at Honeywell DCS system as 0 to 100% of low explosion limit. It will be explained later what does it mean, low explosion limit. NGT, toxic gas detector. At SGP, toxic gases, that is mostly hydrogen sulfide, are detected by Draeger Polytron 2 toxic gas detectors and transmitters. NGH, hydrogen gas detector. Hydrogen is detected by Draeger Polytron 2 toxic gas transmitters, the same as for H2S, but with H2 sensors. NGO, oxygen deficiency detector. Oxygen deficiency is detected by Draeger Polytron toxic gas transmitters, the same as for H2S, but with O2 sensors. Polytron 2 is one universal transmitter for all toxic gases and O2. NMC, manual call point. NSL, visual alarm beacon. NHE, linear heat detector. Linear heat detector consists of two wires cable with a special insulation between wires which shortcuts the wires in case of temperature increase. NFL flow switch is a variable area flow meter with limit switches. It is installed in aspirator cabinets containing flammable gas detectors and measures the flow of flammable gas to the detectors. If there is no flow, a limit switch of no or minimum flow is activated and produces an alarm signal. Explosions and the protections of electrical and instrument equipment in explosive atmospheres. It is a fact that gases, vapors, and mists escape during the production, processing, transportation, and storage of flammable materials in the chemical and petrochemical industries, as well in the production of mineral oil and natural gas in mining and many other sectors. During many processes also, flammable dusts are created. These flammable gases, vapors, mists, and dusts form an explosive atmosphere with the oxygen of the air. In the case that this atmosphere is ignited, explosions take place which can result in severe harm to human life and property. An explosion is the sudden chemical reaction of a flammable material with oxygen with simultaneous release of high energy in form of fire and pressure. Flammable materials may be present in the form of gases, vapors, mists, or dusts. In order for a fire or explosion to occur, three conditions must exist. Flammable material in ignitable quantities, oxygen in the air, ignition source. It is called explosion triangle. The areas where the explosive atmosphere or explosive mixture of gas and air can occur are called hazardous area or hazardous zones. Hazardous zones are divided into zones 0, 1, and 2. These zones relate to the predicted occurrence of an explosive atmosphere in that zone. Zone 0, explosive atmosphere is present more than 1,000 hours a year. A year has 8,000 hours. Zone 1, explosive atmosphere present between 10 and 1,000 hours a year. Zone 2, explosive atmosphere present less than 10 hours a year. there are three gas groups in relation to their ignition energy: 2A, 2B, 2C. The groups are related to the minimum ignition energy required to initiate an explosion. For the group 2A, the minimum ignition energy is 100 microjoules. For the group 2B, it's 60 microjoules. And for 2C, it's only 20 microjoules. Depending on the ignition temperature of the gases, there are 6 temperature classes. T1 with 450 degrees ignition temperature and T6 with 85 degrees ignition temperature. Electrical equipment used in explosive atmospheres must have the surface temperature lower than the temperature class of the gas present in explosive atmosphere. The best equipment is the one with surface temperature lower than 85 degrees Celsius, and it has the class T6. Let us examine protection types of electrical equipment. First, flame-proof enclosure. It is marked by the letter D. It is the type of protection in which components that could ignite a potentially explosive atmosphere are fitted in an enclosure that will contain the pressure of an explosion, preventing ignition of inflammable gas outside the enclosure. Then we have intrinsically safe type of protection, marked I. Intrinsic safety, IS, is based on the principle of restricting the electrical energy available in hazardous area circuits, such that any sparks or hot surfaces that may occur as a result of electrical faults are too weak to cause ignition. Isolators in safe area prevent the flow of energy into hazardous area. Intrinsic safety is the only one protection that can be used in zone 0. Intrinsic safe equipment for zone 0 has an additional letter A, so the designation is IA. Intrinsic safe equipment for zone 1 is designated IB. The third type of protection, called increased safety and marked E, consists of higher quality equipment, and it refers practically to the junction boxes. No electrical live equipment in increased safety junction boxes is allowed, just terminals. ATEX directive. The directive covers equipment and protective systems which may be used in areas endangered by potentially explosive atmospheres created by the presence of flammable gases. The directive covers both electrical and mechanical equipment. Compliance with ATEX directive has been a legal requirement in all European Union member states since July 2003. All ATEX equipment for surface installation belongs to Group 2. Group 2 has 3 categories. Category 1G for equipment installed in Zone 0. Category 2G for equipment installed in Zone 1, and Category 3G for equipment installed in Zone 2. G means gas. ATEX coding of the equipment adds the additional to the current coding practice. AX, explosion proof in accordance with ATEX. 2. Group 2 for surface industries. 2. Category equipment suitable for Zone 1. G. Suitable for atmospheres containing gas. This coding is added to the former coding, for example, EXD2BT4, where E is European certificate in accordance with standards. X, explosion-proof electrical equipment. D, flame-proof electrical equipment. 2, group of gases. B, group 2B group of gases. And T4, temperature class, 135 degrees centigrade maximum surface temperature. So, the example of an ATEX equipment designation above is 2G, EX, 2B, T4. Once again, Roman 2 means surface industries, 2G means group Zone 1, E, European Union, X, explosion protected equipment, D, flame-proof electrical equipment, 2B, group of gases, T4, temperature. Ingress protection, or IP. 2 digits are used to denote the level of ingress protection that a piece of apparatus enjoys. First number refers to solids and the second to liquids. 00 means no protection. S, the number is higher, the protection is higher. For instance, the first number 6 means totally protected against dust. Liquid protection has numbers from 0 to 8. 6, for instance, means protected against strong water jets from all directions. 8 means protected against long immersions under pressure. Parts per million. Parts per million, or shortly ppm, means the number of particles within a million of particles. One apple within million of apples is 1 part per million of million apples. It is usually written 1 ppm. 3 apples within a million is 3 ppm. ppm is used at SGP to denote very small concentrations of H2S within air. For loop checking, ppm is used to denote the range of toxic gas detector, NGT. Percent. Percent means divided by 100. For example, 75% is 75 divided by 100 is 0.75. 325% is 325 divided by 100 is 3.25. X percent of a number means x times a number divided by 100. Example, 12% of 345 is 12 multiplied by 345 divided by 100 equals 41.4. Percent in SGP is used to denote the content of flammable gas in air. 4% of flammable gas in air means that there are 4 particles of flammable gas and 96 particles of air. EL, or lower explosive limit, is the minimum percent needed of a flammable gas in air to support combustion. For example, the LEL of methane, the major component of natural gas, is 5%. Most of the time it is the percentage of LEL that is used. 100% of LEL of methane means the 5% that we just mentioned. 5% of LEL would then be 200% methane in air, etc. Percent LEL is used in loop checking to denote the range of flammable gas detector, NGC.